Alright, in this video, I'm going to be solving the problem of a 2,510 kilogram car driving along a path, a curved path that's slanted inwards at 30 degrees, and the curvature, the radius of the curvature is 50 meters. So this is my graph for it. This is the car. This is it's on a friction. It's on the surface of friction. It's on the surface of friction. And the radius of curvature is 50 meters with a 30-degree slant or incline. And it's 10 kilograms heavy. And the coefficient of static friction between the road and the car is going to be 0.43. All right. So our first steps will be to identify our first step is to make a free body diagram. That's going to be our first step. So we know that, here, let's start with the vertical components. So for our vertical components, we have the force of gravity. The force of gravity will be going down, directly down on the car, with the force of mg. And to cancel that out, we also have not normal force, but normal force times cosine theta will be going upwards. So we have mg going downwards, and then we have normal force cosine theta going upwards. But due to our friction pushing the car up against gravity, or against the natural, want of the car to slide downwards, we also have a vertical component of friction sine theta, which pushes the car downwards, which will be assisting, the force of friction times sine theta is assisting the force of gravity in pushing it down. And those two added together should equal normal force times cosine theta. So we have our two forces acting downwards on the car, mass times gravity, and the force of friction times sine theta. And we have our normal force times cosine theta acting upwards on the car. Now, if we set those equal to each other, the frictional force times sine theta plus mass times gravity, we set it equal to the normal force times cosine theta, we can then solve for normal force. So we do know that the force of friction is going to be normal force times the coefficient of static friction, and that'll also be multiplied by sine theta, which is added to mass times gravity, and that should equal normal force times cosine theta. So this is our first step in the equation. All we did was turn the force of friction into normal force and the coefficient of static friction. So from there, we're going to move normal force into a position where it can be solved. So we'll move the normal force times coefficient of static friction times sine theta to the other side of the equation. And then after that, we'll factor out normal force. So it'll just be cosine theta times coefficient of friction times sine theta. And then we solve that. Normal force is equal to mass times gravity over cosine theta minus the coefficient of friction, or coefficient of static friction, times sine theta. So this is the math that we do for it. So we say here that we move, so here's where we move both the terms that have normal force and on one side. And then after that, we factor out normal force, and then we divide on both sides by this, and we get normal force is equal to mg times, or mg divided by this term minus this term. Now we're done with vertical components. So let's move on to horizontal components. So pushing it down the ramp, we have normal force times sine theta. We have that pushing the car down the ramp. And then pushing the car up the ramp, which is acting against normal force, is going to be the force of friction times cosine theta. We'll be pushing it upwards. So as we can see here, we have normal force times sine theta pushing it down the ramp. So in this scenario, this will be pushing this downwards, and then this will be pushing it upwards. So we can set that equal to each other, assuming that they don't, move, or assuming that it does not slide down the ramp, which is what, the question is asking us to calculate the maximum speed at which the car does not slide, up the ramp, sorry. So we're assuming that they're equal to each other. So let's get them to one side. Now we can say the force of friction times cosine theta minus normal force times sine theta should equal 0. So what this is saying, it's saying that due to the frictional force and the normal force, our car will not move up or down the ramp. So it will be that, so that a net force of both these forces acting on the car moving up and down the ramp will be 0. So the car will stay at one spot on the ramp. That is what it's assuming. So this is where centripetal force comes in. And centripetal force is basically the force that keeps the car moving towards the center. Or, yeah, I believe that's true. It's a force that causes a body to follow a curved path. That is what, Google is saying. And so if that is true, we can set, and we know that centripetal force is just mv squared over r. That is what, we know. So we have our mv squared over r. So if mv squared over r is centripetal force, and centripetal force is the force that keeps a car moving and following the path of a curved, or keeping a body, following the path of following a curved path, then we can assume that F, or the force of friction times cosine theta, what we have here, keeping this car, still, will be equal to the centripetal force that keeps the car, following this path. So we can say that force of friction times cosine theta minus the force of the normal force times sine theta should be equal to mv squared over r. Now, at this point, we're going to need a few numbers to solve for velocity. The first number is going to be normal force. So in our vertical components list, we've solved our equation for normal force. So now all we have to do is plug in the numbers. So we have normal force is equal to, so here, let me show you the equation again. Normal force is equal to mass times gravity over cosine theta minus mu, the coefficient of static friction, times sine theta. That's normal force. So let's just plug in the numbers, see what we get. So mass, 2510 kilograms. Gravity is going to be 9.81. And then we're going to have cosine of 30 degrees minus mu, the coefficient of static friction is 0.43, which is a given. And then sine of 30 degrees. So, okay, let me simplify this a little bit. So cosine of 30 degrees is going to be root 3 over 2. Okay, sine of 30 is going to be 1/2. I'm just going to use a calculator. So 2510 times 9.81. And then we're going to have that divided by cosine of 30 minus 0.43 times sine of 30. So we're getting a normal force of around 42,519 newtons is going to be our normal force. But actually, let me do this math one more time. Here, I'm going to pause it really quick. All right. I've done the calculations, and it is correct. So we find here, after doing a bit of math, we find that our normal force is equal to 42,519 newtons. And at this point, we can plug that back in to this equation to find our velocity. So here we can say that mv squared over r is equal to the force of friction, which is just normal force times this mu, or coefficient of static friction, times cosine theta, minus normal force times sine theta. Now, this is, here it is. This is what we have. So from here, we can either clean this up a little bit, or we can just plug them in directly. So what I'll actually choose to do is to get everything on one side, and then I'll have velocity on the other side, and then I'll decide to plug it in. That's gonna be here. Yeah, that's gonna be my route that I'm choosing. So from here we can say that velocity is gonna be equal to square root of r times normal force times the coefficient of friction times cosine theta minus n times sine theta. All of this will be over the mass. So what we've arrived at is that velocity will be equal to the square root of r times this whole thing right here divided by m. That's going to be our velocity. Now, the m is also in the square root as well. So right here, m is also included. So here, I think I will just plug all the numbers in, and then I'll do the math. So 50 times 42,519. Okay, I actually do not have this. I'm gonna turn the page. So we're saying velocity is equal to square root of r times n u sine theta. Okay, sine theta. Cosine theta minus n sine theta. Okay, all I've done is started it on a new page so I can have some space. Okay, so velocity will be equal to square root, okay, r. Here, r is referring to the radius of the curvature. And we have that down as 50 meters. So when we're referring to centripetal force, the r is going to be the radius of the curvature. And then everything else is, self-explanatory. Mass is going to be the mass of the object, and velocity is going to be the velocity of the object. Okay. So for our radius, 50 meters, our normal force is going to be 42,519 meters. 42,519. And then our coefficient of static friction is going to be 0.43. And then it's going to be times cosine of 30. And then it's going to be all of this minus normal force once again, so 42,519 times sine 30. And we're going to have all of that divided by 2,510 kilograms. Yeah. So here is our equation once we have it all, plugged in. Now, here, okay, now I'm just going to start and do all of the calculations. Okay, let's see. So, okay, 42,519 times 50 times 0.48. Wait, I can just 42,519 times 50, which is the radius, times 0.43, which is the coefficient of static friction, times cosine of 30. And then after that, we're going to subtract that by 42,519, which is the normal force, times sine of 30. And then we're going to divide this number. So the number we got, okay, so the number we got was 183,020 for the top. Top of the inside of the fraction, or of the inside of the square root. Sorry. So 183,020, and that's going to be divided by 2510, which is the mass. So divided by 2510. And then after that, we must get the square. And for this, I'm finding it to be 73. So after this, we get the square root of 73. And our velocity should be around 8.54 meters per second. That actually seems quite slow. I think, here, wait. All right, so unfortunately, I had made the mistake of using degrees rather than radians. So I will quickly rewrite my equation so that it works out. Even though it'll work, I'd get the same answer if all I did was just change it to radians. I'd rather rewrite it into something that looks a little more appealing as well. So we're starting off with this equation of mv squared over r is equal to n mu coefficient of static friction times cosine theta minus normal force sine theta. So we have this equation. So previously we figured out that normal force is equal to this equation right here. mg over cosine theta minus coefficient of friction times sine theta. So rather than solving for that immediately, I will instead pull out the normal force from both of these terms, and I'll do something that looks like this. I will do here. I'll pull it out, and then I'll plug in the terms that equal normal force in for normal force, and I'll multiply it by this, and then I'll make sure to solve for velocity as well. So we know that normal force is equal to mg over cosine theta minus mg over cosine theta minus coefficient of friction times sine theta, and we'll be multiplying that by coefficient of friction times cosine theta minus sine theta. So this is the equation we currently have. Now next is we'll single out our velocity. So the steps we're going to take to do that is we will multiply by r on both sides. So we'll have mv squared equals rmg times coefficient of friction times cosine theta minus sine theta, and that'll all be over cosine theta minus coefficient of friction times sine theta. And then next we're going to divide by m on both sides. So this will cancel out and this will cancel out, and we'll have v squared is equal to rg, or radius, times gravity times the coefficient of static friction times cosine theta minus sine theta. All of this will be over cosine theta minus mu sine theta. Now let me show you the work I've done. So like I said, multiply by r, so we have r up here now, and then we're going to divide by m, so we cancel this out, and we cancel this m out, and then we're left with rg times this over this is equal to v squared. So now we will solve, we'll square root it, and then hopefully we'll get an answer that sounds a little more plausible using radians rather than degrees. All right. Well, first, this is the equation for velocity that I have. And first, we're going to plug in the numbers. So the numbers we have for radius, like I've said before, 50, and for gravity, we have 9.81. And then for the coefficient of friction, we have 0.43, which will be multiplied by cosine of 30, which is going to be subtracted by sine of 30. And this will be for the top equation, divided by cosine of 30 minus 0.43, which is a coefficient of friction, times sine of 30 as well. So I'm going to crunch these numbers and come back. All right, after plugging in our numbers and using radians rather than degrees, I found that the velocity, well rather the maximum speed at which the car does not slide up the ramp, is going to be around 30 meters per second, plus or minus maybe 2 or 3 meters per second. Thank you.